Hello good people, I'm going to talk about classification of matter. In particular, I will look at how we can classify matter according to its composition. In very broad strokes, matter can be divided into mixtures, compounds, and elements. Most of the materials around us are a mixture. A mixture consists of two or more substances that retain their own chemical identity. What does this mean? Well, let's say I take a cup of water and dissolve a spoonful of sugar in it. The cup now contains both water and sugar, two substances. Neither substance has been changed. I still have water, but I also still have sugar. Yes, it is dissolved in water, but it is there. Mixtures also have a variable composition and they are separable into its components. What does that mean? Well, let's talk about sugar in water again. So previously I dissolved 1 spoonful of sugar into a cup of water and I ended up with sugary water. But I could easily dissolve 2 spoonfuls of sugar in a cup of water. I would still have sugary water, but the composition is not the same. Now I would have more sugar. So that is what we mean by variable composition. What about this separable into its components? Well, it means that even though I have dissolved sugar in water, I can actually get both of the substances back. For example, I could place my cup of sugary water onto a stove, heat the water up, the water would evaporate, and I would be left with sugar. I could also collect the evaporated water, which means I would recover the water too. The recovered water and the sugar would be the same water and sugar I started with. In other words, their chemical identity would not have changed. Now it turns out that there are two types of mixtures we could have. They are heterogeneous and homogeneous. What is the difference? A heterogeneous mixture is not the same throughout. On the other hand, a homogeneous mixture is same throughout. And I will look at a few examples in a moment. For now, this is just a quick summary. Apart from mixtures, we can also have compounds and elements. How are they different? Using very broad terms, we could say that compounds consist of 2 or more types of atoms, whereas elements consist only of 1 type of atom. Okay, now that we have some rough classifications of matter and their definitions, let's look at each one in turn in more detail. First up are heterogeneous mixtures. So here we have a few examples. Salad, mixed nuts, a glass containing water and oil, and concrete. So a heterogeneous mixture is not uniform throughout, and often there are visibly distinguishable parts. So for example, if I mix water and oil, 2 layers will quickly form. The oil will float above. So there are quite clearly 2 distinguishable parts or 2 phases. When I have a bowl of mixed nuts, the nuts are not mixed uniformly. That is to say, I might have 2 almonds next together here, and then maybe a cashew over here, and then 3 almonds next together over there, and then 3 cashews over here. So it is not uniform. The same goes for a salad. It is not uniformly mixed. Concrete is a little bit trickier. It does look uniform. However, on an atomic scale, things are a little bit different. So, let's look at the atomic scale of a heterogeneous mixture. So let's say that the blue and orange spheres represent different components of a mixture. The spheres are not mixed evenly through. I have sections where I have more blue spheres, and I also have sections where I have more orange spheres. So when I have a heterogeneous mixture, sampling from different locations will give different results. To go back to the macro scale, the visible scale, if I look at this cup with water and oil, I will get a different result if I take a sample from here. This sample will contain mostly water, than if I get a sample from up here, because this sample will contain mostly oil. In a similar fashion, if I was to sample the salad, if I take one sample from here, I will end up with a tomato, whereas if I take a sample from here, I might end up with a piece of lettuce or celery. Alright, so how does a heterogeneous mixture differ from a homogeneous mixture? Well, let's have a look. Firstly, let me get rid of this and bring in some homogeneous mixtures. So here they are. We have apple juice, mayonnaise, air, and brass. Homogeneous mixtures are also known as solutions. So in everyday language, when we think of a solution, we think of a liquid. However, in chemistry, we can have liquid solutions, solid solutions, and gaseous solutions. So apple juice is an example of a liquid solution, whereas air is an example of a gaseous solution. Brass, on the other hand, is an example of a solid solution. Solid solutions are also sometimes referred to as alloys. So how are homogeneous mixtures different from heterogeneous mixtures? Well, they are uniform throughout. This means that all sampling locations will give the same result. On an atomic scale, a homogeneous mixture looks a little bit like this. The distribution of different particles, in this case orange and blue spheres, is uniform. Brass is a solid solution or an alloy of copper and zinc. It is also a homogeneous mixture. This means that if I take a sample from here, and maybe another sample from here, or even another sample from over here, I should always end up with the same amount of copper and zinc atoms. In a similar fashion, air is a homogeneous mixture of oxygen, nitrogen, and argon. Roughly speaking, air is 78% nitrogen, 21% oxygen, and about 1% argon. And because air is a homogeneous mixture, no matter where I take a sample from, so maybe here, or down here, or maybe up here, I will always end up with these same percentages. 78% nitrogen, 21% oxygen, and 1% argon. I will not encounter a situation where one sample contains only oxygen and another sample contains only nitrogen. They are all mixed evenly throughout. Alright, let's look at compounds next. A compound is a substance with a constant composition of two or more different types of atoms. Unlike an element, a compound can be broken down into simpler substances by chemical means. Examples of compounds are sodium chloride, commonly known as salt, mercury iodide, water, and copper sulfate. Most of the chemicals that chemists play with are in fact compounds. How do they differ from mixtures? Well, remember, mixtures are combinations of two or more substances, whereas compounds are combinations of two or more different types of atoms. How does this look on an atomic scale? Well, let's bring it in. So on the left, in case of sodium chloride, we have a combination of a sodium atom and a chlorine atom. The chemical formula for sodium chloride is NaCl. We will talk about chemical formulas later on. For now, you need to know that each type of atom has its own symbol. In case of sodium, the symbol is Na. In case of chlorine, the symbol is Cl. In case of mercury iodide, two iodine atoms combine with a single mercury atom. The chemical formula for mercury iodide is Hg, indicating the mercury, I2, indicating the iodine, and the little 2 in the subscript tells me that there are two of them. In case of water, we have a single oxygen atom that is bound to two hydrogen atoms. And the chemical formula is H2, indicating the two hydrogens, O, indicating the oxygen. Finally, in this list of examples of compounds, we have copper sulfate, which is made up of one sulfur, 4 oxygens, and a single copper atom. The chemical formula for copper sulfate would be Cu, indicating the single copper atom, S indicating the sulfur, and O4 indicating the 4 oxygen atoms. Please note that all of these spheres that I have drawn do not necessarily represent the reality. They are just a way that we can imagine these compounds on an atomic scale. And there is far more to this story, which will be explored in later videos. Also note that aside from their atomic composition, compounds can differ in other ways too. And as it turns out, sodium chloride, mercury iodide, and copper sulfate have far more in common with each other than they do with water. But more on that much later on. So how can we quickly distinguish between a compound and a mixture? Well, generally speaking, if you can write a distinct chemical formula for something, you are dealing either with a compound or an element. If you cannot write a distinct chemical formula for the substance, you are dealing with a mixture. Finally, when it comes to compounds, please note that although we can break them down into simpler substances, that is not always easy. So yes, water can be split into hydrogen atoms and oxygen atoms, but it does not mean that it happens easily. Alright, so now let's look at the elements. An element is a substance that contains only one type of atom, and it cannot be broken down into simpler substances using simple chemical processes. So some example of elements are gold from my private stash, mercury, iodine, and sulfur. So although all of these are examples of elements, on an atomic scale, they might look a little bit different. So let's explore that for a moment. In case of gold and mercury, on an atomic scale, we have single atoms. The chemical symbol or chemical formula for gold is Au, whereas the chemical formula or the chemical symbol for mercury is Hg. So when I have a bar or a lump of gold, I have a whole bunch of individual single gold atoms bunched up together. What about iodine? Well, on an atomic scale, iodine is actually made up of 2 iodine atoms. And so the formula for iodine would be I, and then in subscript a little 2. So when I have a lump of iodine, I have a whole bunch of iodine pairs bunched together. In case of sulfur, it gets even more interesting. On an atomic scale, sulfur will form clusters of 6. So the symbol would be S for sulfur and then a 6 in the subscript. So when I have a pile of sulfur, I do not have individual sulfur atoms, but rather they cluster in groups of 6. And then those groups of 6 will bunch together to give me my pile of sulfur. Please note that even though we cannot break an element into a simpler substance, that does not mean that there is nothing beyond the atomic scale. In fact, atoms have their own fine structure, and we can talk about the subatomic scale, and in fact we will in future videos. So in summary, matter can be classified according to its composition. And this time, starting from bottom, we could say that we have elements which consist of only one type of atom. For example, iron, gold, sulfur, iodine. We have compounds that consist of 2 or more types of atoms. So water, sugar, salt, mercury iodide, and so on. And then we have mixtures. Mixtures consist of 2 or more substances that retain their own chemical identity. So I could dissolve some salt in water, or I could dissolve some sugar in water, and I would end up with either salty water or sugary water. However, I do not lose water, nor do I lose salt, nor do I lose sugar. I can still recover all of those components. When it comes to mixtures, we also have 2 types. Heterogeneous, which are not the same throughout, and homogeneous, which are the same throughout. In case of a heterogeneous mixture, samples taken from different locations will yield different results. whereas in case of homogeneous mixtures, samples taken from different locations will yield exactly the same results. So a mixture of water and oil is a heterogeneous mixture, whereas air, or even that salty or sugary water from before, are examples of homogeneous mixtures. No matter where I take the sample from, I will end up with the same percentage of components. In case of air, it means that I will always end up with 78% of oxygen, 21% of nitrogen, and 1% of argon. And in case of salty or sugary water, no matter where I take the sample from, I will always end up with the same concentration of salt and the same concentration of sugar. That is all for now, and I will see you on the flip side.